And I will just give you an overview of some tools we've developed recently to work with electrophysiological data, and that it's all in a way oriented to the greater goal of being able to move stimulation and medicine delivery into a more closed-loop system, moving far away from an open loop, which is the paradigm we have now. So what I will talk about is why do we need these tools, why do they have to be open source, and why we chose to develop them in C and C++. I will present both of them. One is involved with analyzing peripheral sensor data, in this case electromyography, which typically records activity from the muscles. And then we'll talk about another tool that is actually intended to do advanced analysis of electroencephalographic data. And after that, I will talk a bit of what's next. So why do we need these tools? First of all, the first app we developed to analyze electromyographic data arise from the need to actually have such a tool, because there isn't any specific tool to analyze electromyographic data which is specific to data produced by electric or magnetic stimulation. So there are several techniques that are quite in vogue now to study the integrity of the corticospinal tract, which involve delivering electric or magnetic stimuli either to the brain or to the peripheral nervous system. So those produce a very characteristic response known as motor evoked potential, and there is, as I said, no specific tools to deal with them. There is out there commercial software that you can use, but it's not specific. So usually this means that what they provide is in a way inflexible. You don't know what's going on in the background because obviously the algorithms are not disclosed. So you have to rely on that what you're doing is okay. The other problem is that typically this involves quite some knowledge. These tools require a lot of knowledge of how they work. So for clinicians and researchers, it's usually a burden to have to deal with those. There is some other tools that are open source, but are typically developed within the MATLAB programming environment, which is a great programming environment. It actually offers a lot of nice features. It's very easy to use relatively. And there is many tools that are developed that are widely adopted, like EEG Lab or ERP Lab, SPM or Filtrip. These are widely used by all the research community to deal with electroencephalography data or MEC data, magnetoencephalography, MRI, fMRI, and so on. However, as I said, these are developed within MATLAB. This means that you first need to own a license of MATLAB, which is usually quite expensive. It is true that most academic institutions do have these licenses, but individual researchers, people doing a master thesis, or clinicians, they may not have access to this. Plus, certain degree of programming is actually needed to use them. The other point to make it open source is that all these tools are great because the whole research community is involved in its development. So whenever a researcher comes up with a new method to actually make sense of the data, they can easily just implement this into these tools. So why do we use C or C++? Well, why not? We could use many other languages, but I would say the nice features of this one is that it allows to code things that are highly efficient, very fast to implement. That the execution time is very fast. It's quite flexible. You can really do pretty much what you want. As it is a very low-level language, you can interface with multiple devices. You can interface with different other software. You can do it multi-platform. Cross-platform. You can have it in a phone. You can have it in Linux, Windows, Mac. The other point is that you can also do multi-threading applications, so you can use the power of parallel computing to try to speed up all these computations. And it's free of charge, of course. The idea here is that these features would allow us to actually develop software or libraries for analysis that would, at the end, enable online analysis. So while we are recording data from a peripheral sensor or from any kind of recording system, we can actually process this data and then get an estimate of what's going on, and then in consequence trigger a device or trigger an infusion device or trigger a stimulation device or make some kind of inference of what's going on, but in real time. So that would be this closed loop paradigm, which we will hear more about later on with András. So, of course, there is some problems with this using C and C++, which is that it's for its flexibility a bit of a difficult language. So you may easily actually produce the opposite of speed, flexibility, and multi-threading if you are not very careful. But hopefully we will overcome this. So the first tool I show you is this motor evoked potential analysis software. You can now download it in the Cambridge Electronic Design Limited webpage. They have a section for research, academic research contributor software, and you can find it there. These guys manufacture high-quality research equipment for gathering electrophysiological signals. So this tool, what it does, I won't go in a lot of detail. If you want to know more, you can ask me, or you can download the app and check it, or you can read the extended abstract, which has much more detail on this. But essentially what this allows is actually to fill this gap. Researchers now can use these common data acquisition systems. They can get their data, and then they can just load it into this software that will kind of do most of the job for them. You can either have two modes. One will allow you to just look at the data visually, trial by trial. You will use these vertical bars that you move around to basically make measurements of anything that is in between. What you see here now, it's a signal. Here you have the artifact produced by some kind of external stimulation, electric or magnetic. And here you have the motor evoked potential elicited on a muscle. So what we can get from here is several things. We can get amplitude, so how much is there from this peak to this one. We can get latency, how long does it take to go from the electric stimuli to the actual response. So how long does it take for this stimuli to travel the nervous system. We can get many other measures. And these measures are actually provided in this software. So when we click measure, this will be stored. The other way you can do this is do it completely automatically. We implemented a series of routines that try to be smart about understanding how each new data that comes in is, and then it figures out what is the best way to deal with it. So if you do this automatic processing, you can process an entire pool of subjects at once without having to really look much at them. And you'll end up with an output which is similar to this thing here in the background. So you will get the most basic measures that are now recognized in research to be of use for this type of data. So you have this amplitude, you have log transform amplitude, you have standard deviations, means. The idea is that once you get this, you can input that directly into any statistics software and get actual final conclusions about what's going on with this data. So that's one app. The other, which is now still in development, it's a bit more complex, it's about analysis of electroencephalographic data. As I said, the main tool now to do this is this open source EEG lab software. However, a certain degree of programming is needed, so usually clinicians and certain researchers may have troubles with that. The other problem is that it's embedded in MATLAB, so you must own that. So we developed this to, in a way, try to supply these gaps. So at the moment, this is just a proof of concept. What it does is something which is actually also missing in EEG lab at the moment. It has some of these facilities, but not those particularly. So what this shows here is time frequency analysis of the electroencephalogram. So we have an EEG, a stream that is epoched. There is some kind of task, like the one Indrek has shown before. And then every time there is this task, there is some kind of brain response. So if we average all these single trials, we get some kind of general response to the stimuli. So if we assume that this stimuli comes at 0 here, and if we decompose, so this signal here is what would come out of this electroencephalogram, this superimposed black line. If we actually decompose this in the time frequency domain, we can see things that are actually hidden to us from the simple signal. We can see things that are, we can see, for instance, the total power, so how much power in the different frequency bands is expressed in this potential. We can see how the phases of this oscillation change with these events. We can see which frequency bands and power ranges are actually influenced or dependent on these phase characteristics. So this is a whole lot of useful measures that gives quite a deeper insight into what's going on in response to a task. So this app now allows you to, you load, I forgot to say, maybe one of the main points also of these apps is that they also come with a library interface to actually get data from many common systems. So in this case, we interface this with MATLAB data types and with this EEG lab and ERP lab data set types. So you can now load those directly in here without having to go there first. So the simple things you can say, okay, I want to see this channel CZ, I want to select a particular experimental condition in this data, I want so many frequencies from this one to that one, I want to decompose with these parameters, this is what's going to be my baseline to normalize the data, and I want to see this time range. So these are now the facilities that are available. The next step, of course, will be to implement more and more of the features that are available in EasyLab and try to add the EMG analysis into it so that we can correlate these two and see if we get even a deeper insight into what's going on. The idea here also is that then implement parallel computing to all these tools to make them really fast so that we can directly use them while we are actually recording the data, so that we can then use that knowledge to either trigger some kind of device or to change whatever it is we are doing with a patient or a subject in an experiment on real time. So basically you could say the greater scope of things will be this one, to actually produce a library that allows recording, analysis and triggering of other equipment at the same time. Applications, of course, will be right now just to allow basically medical and experimental concurrent sensor recording, so you can have many sensors, record all together, do some kind of quick analysis and put all this data in relation. The other, of course, a bit more sophisticated would be to then use that knowledge to feed it back into whatever it is you are doing, the intervention, and try to improve it online. So thanks for your attention.